Hi, in this video I'll give an introduction to Moldex3D Stress, not the whole with annealing and so on, but how to put up a normal strength calculation or static deformation. Moldex Stress has some different possibilities. There's a normal FEM analysis where you bend a beam or put on some load with some constraints, boundary conditions. And then the other thing is you have annealing, where you see the long time effect of putting on heat. Yeah, for example, heat. But in this case, it's only the normal strength calculation. First step is just setting up the analysis. This is a Moldex3D 2025 release 2. So I'll start with a mesh, and for this I want a pressure out here and clamping down here. I need a gate, even though I really don't need it, but I need to have it. There's two different ways you can do the simulations. You can either do a simulation, traditional fill pack warp, or also with cooling, and then a stress on top of that. Then you can include all the effects that you've got from the injection molding process. This, if you have a linear material, or sorry, not linear, material without fibers, it has not such big effect. But if you have a fiber-filled material, it has a huge effect if you run the filling and packing a warp before you do the stress analysis. Okay, but in this case, I'll just do the fast one. So we don't have to put up a process and so on. What I need is a gate, and I want around the gate there will be some mesh optimization because of the injection molding. So I'll put the gate, if I only want to run stress analysis, I put the gate a place where it has no effect on the stresses, because the amount of elements are important when you do strength calculation. I'll just put a gate here. Doesn't matter which size or whatever. And then I'll put a mesh on seating there. And I'll make it quite fine, because if I have to rely on the stresses, then it has to be a fine mesh. Not all over the part, but in this case, the simulations are so fast, so it's not a problem if you run a normal linear simulation. So the stress, when I say normal linear, the stress, Moldex stress, covers primary small deformation and only linear material data and no contact analysis. So you have to describe your boundary conditions with the traditional forces and pressure, and also with some constrained fixed boundary conditions. I'll go for this. I think then I'll do this. Yeah, I think it's okay. For the mesh, I just use the 5 boundary layers, because then I have enough mesh through the wall thickness. If you don't have enough layers of mesh through a wall thickness, the stiffness of the part will be too high. And of course we want quite a flexible part, so we have a converged result. I'll just generate the mesh, the solid mesh. Like this. Yeah, do the final check. Doesn't matter how I do it. And what I want here is I'll put on a pressure out here or force, and then I'll clamp it at the end. So now I have this, then I have to add a material to it. I'll just take an ABS in this case, like this. The process, I'll just click it and say next, 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 finish. Don't care what's in it. And then I'll double click here and use the stress, save. And for the computation, I'll wait because I will put on some boundary condition. In the home here, I have the boundary conditions. And if I wanted a pressure, I could put on force out here. And if I want a force of hanging 1 kilo pointing downwards out here and clamp it totally here, then I can choose, if I choose a force, I have to count the amount of nodes in the area, and then I will sum up the forces that I put on each node. It's quite not very flexible. So I always, nearly always, use pressure. So I will have a pressure on this surface that is the same as the force. So let's say what would have 1 kilo here. And then I start inspection, distance, start to measure 28 and 28. So if I go out here, I want 1 kilo, just approximately 10 Newton. Then I have the pressure, I have the force, and I divide it by 784, which is 28, the area of the surface, and I get this pressure, also the same as megapascal. So I'll just put on a pressure. I'll go back to our boundary pressure, and if I hit here, it takes the whole thing, but I'll just keep. I can see the line, straight line is running approximately here. So I'll keep control down and ALT. Oh. And then I'll just deselect. So I have the correct pressure area. You could also extrude this a bit up, then it will be disconnected from the rest of the surface and it's much easier to pick it. But anyway, I'll just put in the pressure 0.127, like that. If you put in a minus pressure, you don't push down, but you'll just pull up. So you can just put minus in front of it, not a problem. And then I'll put a fixed constraint on this one. Normally, if I'm concerned about the stresses in the area, I need it to be constrained in 3 directions, and it may not also rotate in the 3 directions. But in this case, then if I want quite okay clamping, I don't use I use the fixed constraint, but I only use the fixed constraint in, let's see, where in the Y direction, like this, and then I pick the nodes now, okay, and then I got pressure here and the fixed constraint here. Now it can't move back and forward. That's okay because it's clamped to a wall, for example. But it can move sideways and up and down, and up and down, yeah. So I need to clamp it. If I clamp everything up and down, it will not be able to move the corners, because when you bend one like this, it will actually get narrow in this area. And if you clamp it totally here, you'll get some wrong stresses in the corners. So this is the hard thing about structural analysis, is to get some boundary conditions that have don't give any not real stresses. So I'll take a fixed constraint again. So instead of having the whole thing, I'll just use Control to deselect. I'll say, okay, this line I will fix in that direction. Okay. And then I need some fixed line in, or fixed point in X direction, but I'll just choose the top down. So I'll go down here, so I don't pick too much, and I'll shoot for this line, fixed constraint. I get a bit too much, Alt and Control down, and then you can start the deselecting like this. And was it X I said? Yes. Okay. Like this. Now I actually have this clamping, and I'm ready for the computation. Fill pack. If I don't run the fill pack, it's not a problem. You can actually build up your own process. If you say customize here, I can remove this. I can put over fill down, pack, warp, down, and say save, stress 1, save, and then I run this sequence in all in all, but I just only want the stress. So I go back to computation, and here I'll just run through it. We have stress analysis type, and then we have a pressure load. We can't take it on or off. You have to delete it out in the model tree. And yeah, then you can go in and say welding angle, which kind of strengths does that have? Of course, that makes sense. If you have a weld line, you can reduce the stiffness in that weld line and see how it behaves. This is one thing. Now it's a linear analysis with linear elements. But if there's the annealing, you can choose that. But if I choose a nonlinear stress analysis, then I can choose element type. I can go from linear to quadratic elements type. And that means that you are able to get a better stiffness of the part without so many elements, and you also have a better representation of the stresses with less elements. But choosing the quadratic takes time. You can also use this one. Then, for example, if you have chosen too big load out here, it will give some, if you don't have the nonlinear, the load will not follow as a normal to the surface during the bending. I will show that later. But normally I would say go for these two if you have bigger deformations. You can also put this on. Then it takes just 5 times as long as for the calculation as here. In this case, it's small deformation, I know that, so I'll just go with the default, say OK, and then I'm ready to run the analysis. I can just try to run it. I'll just, in this case, use a local host connect. I'll go down so I don't lose my power on my computer. And it takes no time doing these kind of simulations. Okay, 23 seconds or 26. So I have now I have the results, and I have the total displacement here. If I look at the results, I'll hide this, and I can see the deformation. It bends downwards 0.17 millimeters, and you can go, I don't know, von Mises stress is okay for, good for steel normally in the linear area. You can say, okay, if in some cases I will look at the maximal principal stress, but I can't dig into that too much now. So if I look at the, let's just say the von Mises stress, you can see I have no stress concentrations. I have a bit down here, so that's the forces in this direction. Maybe I should have clamped it a bit on more nodes to avoid this, but anyway, it's okay for this. I can just scale it and say I rely on these stresses because I don't have anything weird up here. But if I go back to total displacement, what I'm looking for is, you can see here, by applying the force, you actually moves it inwards. If you have clamped it totally in X, Y, Z in these corners, you will introduce some stresses. I'll show that to you later. This is actually how you do it. I'll show this about clamping. This one I have clamped X, Y, Z in all directions. So if I look at the deformation, you can see, I'll try to scale it, and it's a big deformation, 13 millimeters, and you can see, it's clamped here, so you get some unnatural movement there. So if I look at the stresses, you can see I introduced some not real stresses maybe in that area. Or maybe I have these stresses, I don't know. But the clamping is 100% clamped. It's not like something moving a bit, or it's a bit just high stiffness. No, it's infinite stiffness. So if I have this stress, where I did the clamping as you saw before, I have my stresses as expected. And if I go to deformation, I can also scale it here, and you can see, yeah, now I have this. But anyway, you can see there's the bending is a bit too high. And if you get something that swallows up like this, you know that the deformation is a bit too high as a normal linear analysis. without any increments where you step down like the nonlinear I showed before. So here I have another example of a highly deformed bending with too much. You can see here this. I put on a pressure here, clamp here. You can see it gets longer than this up, and I don't think that's real. This is scaled one time the deformation. But if I use the nonlinear, I can actually get something that's much more real, because it puts up the loading in in this case, 4 increments. So you can decide by yourself and say, okay, when I'm here in the calculation, I update the pressure so it doesn't move downwards, but it moves as a normal to the surface, and so forth until it's down here. It's more realistic, but still the deformations are too big for a normal linear simulation, I would say, because you'll end up with plastic deformation before you get this shape. And the last thing is the stress. When can you rely on the stress? I've done a small one here. Oops. A bending down here. And what I'm interested in, of course, the stress here. And the stress should then be compared maybe to maximal allowed stress or some yield stress or whatever. What is your design criteria? If I look at the stress here, you can see I got some quite okay, not jumping too much in the colors from element to element. And you need, especially if you have linear elements like we have, you need quite many elements in a blend like this, where you have a stress concentration. Even though you don't need it for the flow simulation, it's recommended to have minimum 8 elements over the wall thickness. In this case, I have a mesh like this. I'll just go out of the scaling. This, you can see it. From this point to this point, minimum 8, but better 12, 16, like this. To have a converge the results of the stress. Okay, that's it. Thanks for watching. Bye bye.